We're going to continue our discussion of work, but we're going to start talking a little bit about energy today too. Energy is a very important concept, and we'll get into what energy is. But what we're going to do mostly is relate work and energy. Talk about how they are a lot alike. So we're going to see how work changes kinetic energy. We're going to see how a bunch of forces acting on something make up the net force and the net work acting on an object, and how that changes kinetic energy. And we're going to apply this work energy thing to look at how work specifically changes the velocity of an object. So before we get going with that, we're going to talk about work just a little bit more. I want to do a clearer definition of work. We're going to do work anytime we use a force to move an object. So it's what happens when a force moves an object. So let's real quick look at three objects. And we'll talk about forces acting on those objects. For this one, we're going to say my force is this way. For this one, we're going to put the force backwards. And for this one, we're going to put the force at an angle. Let's see here. And each one of these objects is going to have a forward displacement. Running out of room there, sorry. So, in the first situation, I see that this force is moving this object this way. That gives me positive work. And if that's the only force acting on my object, we speed up. Velocity increases in the direction of the force because it's with my delta x. Now, here, if I'm moving forward and I apply a force backwards, that's going to take speed away. That's what we call negative work. That force is working against the motion. It's trying to stop the object from moving. So it's sort of the opposite of the force moving an object. This is a force stopping an object. That's why we have it as a negative force. And in this case, we're going to slow down. And this is where the cosine theta thing came up last time. Looking at this force, not all of this force is making this object move. In fact, only the horizontal part, or the x part of my force, is getting this object to move anywhere. So when I look at the work done by this object, it's just the force in the x direction times my displacement in that direction. That's how I do it. I do not care about the work done by the force in the y direction. That does not contribute to the movement. That does not contribute to this thing moving at all. It doesn't hurt me like negative work, and it doesn't speed me up. It doesn't help me like positive work. Now, that's just some things I wanted to get into with work before we start talking about energy. Now, there are a bunch of different kinds of energy. Mechanical, chemical, heat, electrical, electromagnetic, and nuclear. I am not going to talk about a lot of those today. We will get into heat, electrical energy, and electromagnetic energy at some point, just not today. What we're going to be spending our time with is mechanical energy. Okay. Now, mechanical energy comes in two forms. There's motion energy, and then there is position energy. We will talk about position later. Okay. Motion energy is where we're going to spend some of our time today. Motion energy, the other way we say that is kinetic energy. So we're going to use a KE to represent that, kinetic energy. That's motion energy. Kinetics is things moving. So kinetic energy is the energy of motion. And just to get us ahead here, kinetic energy as a formula, if I wanted to calculate it, is 1/2 the mass of an object times the velocity of an object squared. That's how we calculate motion energy. So it has something to do with mass moving, but it has more to do with the motion of an object than it does with the mass of an object. The velocity is very important for kinetic energy. It's squared. That has a very big bearing on the size of our kinetic energy. Okay, so kinetic energy is the energy of motion. Change the motion, we change the kinetic energy a lot. That's kind of what we're into now. The work energy theorem says that work is the thing that can change the kinetic energy of an object. Okay, so positive work, that's our force in the direction of motion, increases kinetic energy. Negative work decreases kinetic energy. And that's great because we said that this increased speed and that this decreased speed. So, because kinetic energy is 1/2 mv squared, if positive work increases speed, it has to increase the kinetic energy. And if negative work decreases speed, if this gets smaller, then my kinetic energy gets smaller. So, what we're going to do with these, well, let me get this out of the way. What we're going to do with those three equations is look at, find a way to relate work to kinetic energy. Okay, so this is our equation that describes velocity and displacement. This is how acceleration is related to force, and this is how work is related to force and displacement. So if we put all three of those things together, just follow. It's not a hard process. So it's not a hard process for you. It's tough for me, apparently. So if we look at this and we substitute acceleration, which is force over mass, into this equation, so we're going to stick it here, what we see right over here is that v squared equals v0 squared plus 2 times force over mass times delta x. Now this force over mass, this force times delta x thing should look familiar to us. It's this right here. So instead of writing force times delta x, we're going to rewrite this thing as v squared equals v initial squared plus 2 over m, that's what we have left over, times work. Okay? And what we're going to want to do is solve this whole thing for work, because we want to see what work is all about. The first thing we're going to do is move over the initial velocity, just subtract it over. Then we want this to go away on this side, so we multiply both sides by, let's see if we can do this in red, multiply both sides by m over 2. So we're going to multiply this side by m over 2. So that makes this go away. And what we end up with for now is mv squared times 1/2 minus 1/2, we're going to distribute that all the way through, and mv0 squared. And that's going to be equal to our work. Now, looking at this and knowing what kinetic energy is equal to, what we have is kinetic energy final minus kinetic energy initial is equal to the work done on an object. Now, I want to be very clear. I skipped a step. That is the net force acting on my object. So this has to be the net work acting on an object. So net work is going to change the kinetic energy of an object. And that's just looking at net force. So net work changes the kinetic energy on an object. We're going to look at that in our next slide. So net work is the work done by all of the forces acting on an object. So let's say we have an object, our standard box. Let's say we have 3 forces acting on it. Force 1, force 2, and force 3. And let's say that our object moves in that direction, in the direction of force, and it's hard to see, 2. Okay? What we have to do if we want to find the net work acting on the object is look at the work done by force 1 and the work done by force 2 and the work done by force 3 and add them all together. By adding them all together, we get our net work. So in this case, force 2, I screwed up our numbering. That is supposed to be force 1. Force 1. So, and our delta x is supposed to be in that direction. So, work 1 is going to be force 1 times delta x, because force 1 is in the same direction of delta x. Work 2, here we see that force 2 is perpendicular to delta x. And we know that that means that the work is equal to 0. I'm not doing any work. That isn't helping me move. And work 3, well, we get the same thing. Force 3 is perpendicular to delta x. You know, big old goose egg as well. So the net work on this object is just equal to force 1 times delta x. And we could use that quantity to determine what's going on with our kinetic energy or our velocity. So let's think about net work being done on an object that's moving at a constant velocity. And before I talk about the solution, I'm going to let you answer, what is the net work being done on an object moving at a constant velocity? Give it 10 seconds. Now, constant velocity should set off a couple of alarm bells for you right away. First one being that the acceleration is 0, meaning that the net force is equal to 0. Now, I know that net work is equal to net force times displacement. Well, if my net force is 0, then all of that's going to be 0. So constant velocity should also tell us that net work is 0. On the other hand, we could also say that work is equal to my final kinetic energy minus my initial kinetic energy. But if I have a constant velocity, the initial velocity and the final velocity are the same. So my initial and final kinetic energies are equal to each other, also telling me that the work is 0 anytime we move at a constant velocity. Now, here's an example that's going to have us look at net work and kinetic energy. So, we have a box, and we're going to draw all the forces acting on this box. All right. First thing we know is that we have an 80 Newton force acting to push the box. It's a 5 kilogram box, so we know that it has weight. Because the 5 kilogram box, we know that weight is 50 newtons. We have a normal force acting on the box. Since it's sitting on the ground and not on tilted ground, and we're not pulling up at an angle, that normal force is also going to be equal to 50 newtons. And we know that there is friction acting on my box. Now, before we move on, we probably should figure out how much that friction is. If you recall, friction is mu times the normal force. Well, that's just 0.5 times 50. So my frictional force here is equal to 25 newtons. All right. The next thing we need to note is that this box is going to move 10 meters in that direction. Forward 10 meters. 80 newtons pushes it 10 meters forward. So, for part A, how much work is done by the normal force? So the work of the normal force, well, we see here that the normal force is perpendicular to my displacement. So that force doesn't help me with this motion at all. That force does 0 joules of work. How about the work done by the force of gravity? Well, we got the same thing. Gravity pulls straight down, we move straight over. So the work done by gravity is also equal to 0 joules. Now, the work done by the 80 Newton force. Looking at the 80 Newton force, well, that is with my displacement, so it's going to be positive 80 newtons times 10 meters. It gives me 800 joules. And the work done by friction, well, friction points backwards. My displacement is forward. Friction is hurting my displacement. So the work done by that is going to be negative, and then the magnitude of that force, 25 newtons times 10 meters, or negative 250 joules. So that is the work done by each one of these forces individually. If I wanted the net work from this, and that's the next part of the question, I'm just going to show you a different way on the next page. The net work, I'd have to add these all together. 0 plus 0 plus 800 minus 250. The net work, nope, not 500, is 550 joules. That is the net work done on this object by all of these forces. We took and added them all together. That's one way to get to the net work. The next part of this question, same question, still asks what's the net work being done on the object. So just to give us a little bit more room, looking back at our free body diagram, we had 80 newtons this way, 50 newtons this way, 50 newtons down from gravity, and friction was pulling back at 25 newtons. Looking at our free body diagram, the 50 and the 50 cancel each other out. And if we wanted the net force acting on our object, 80, 25, it would be 55 newtons. So we could also calculate net work by taking our net force times the displacement. Well, that's 55 newtons of net force times 10 meters of displacement. Do it again. 550 joules. So, why is this net work less than the work done by this force? Friction. We lost work we put work into beating friction. That's why it's less than that 80 Newton force. Now, the last part, if this block started from rest, what's its final velocity? Well, let's use the work energy theorem. Work is equal to the change in kinetic energy, or work is equal to 1/2 mv final squared minus 1/2 mv initial squared. Now, if we started at rest, that means v initial is 0, so the initial kinetic energy is 0. So my work is equal to 1/2 mass times velocity squared. So my work, 550 joules, is equal to 1/2 times 5 times velocity squared. So, little mathematical magic. I'll let you work on that on your own. As I pull out my calculator. Multiply both sides by 2. Divide both sides by 5 and square root it. And when we do that, we get the velocity to be 14.8 meters per second. Now, that's not the only way we could have found this velocity. We also could have used the second kinematic equation. I'll let you do that on your own. And for now, that's it for work and energy.